Welcome everybody. Welcome to the second part of the third lesson. So after covering what are correlated and uncorrelated network, we want to go back to the maximum entropy ensemble of network which have the degree sequence as a constraint and check what happens in presence or in absence of the structural cutoff. Sorry. Let me see. Okay. So we start with the canonical ensemble and we consider the expected degree sequence as a constraint. So practically our constraint is that for each node we have a set of n constraints, and for each node we fix that the number of links ending to the node I in average over the ensemble should be equal to k bar I. Okay, so k bar indicates our the degree of node I that we want to achieve in expectation over the ensemble. So we have discussed this ensemble in the previous lesson. The probability of the graph is a probability assigned to every adjacency matrix and has this exponential form, typical of exponential random graph, where we have Z, which is the partition function, and the Hamiltonian includes one Lagrangian multiplier for every constraint, so lambda I for each I, and then multiply by the observable that we constrained, which is here the sum of the link ending to node I, so it's degree essentially. So in this ensemble, the marginal probability that I connects to J can be evaluated in this way. So we have the probability of the full network in the ensemble, and we ask ourselves what is the average value of the element of the matrix IJ, indicating if there is a link or not between node I and J. And this marginal has this form that is a kind of yes, is also called Fermi-Dirac form or logistic form, and is not factorized into element only depending on I and only depending on J. Okay, so this is a first insight that here in this model, if we don't do any approximation, we will get some degree correlation, because we have seen that the marginal of a link in an uncorrelated network is just Qi, Qj. So it's factorized in terms only depending on I and only depending on J. Instead here, this expression is not. And we see that the constraint is the constraint that fixes the Lagrangian multiplier, is that in expectation, the degree of node I is given by this quantity. Okay, so this expression for the marginal, as I mentioned to you, leads to natural correlation. So there are correlation, because this is not factorized into term only depending on I and only depending on J. There are correlation here in this ensemble, and these correlation are disassortative. And these are due to the fact that in general, if I have a degree distribution which doesn't have a structural cutoff, what I have is that I want to have a simple graph, because by construction with maximum entropy, I construct a simple graph. But, so I need to avoid having multiple links. So I do that by linking preferentially high degree node with low degree node, because otherwise I will have multi edges. And so this can be measured. So you can construct this maximum entropy ensemble, and you can study the correlation in that, and this is a version of the randomized world trade network, and here you see that you have this associative correlation popping up. So this happens when the maximum degree of the node it's larger than the structural cutoff. In order to have the uncorrelated limit, you need, in order to have the uncorrelated limit, you need to have a maximum degree which scales like square root of n, so that you need to impose the structural cutoff. And in that limit, the expression for the marginal that we have seen that, you know, is in general not factorizable into term depending only on I and term only depending on j, can be approximated by this expression, exactly Pij in the uncorrelated limit, so it can be factorized. So how can we see that? So this is the limit in which e to the minus lambda I is very small. So in this limit, I can consider here the denominator and neglect the second term respect to 1. And in that case, I will be left only by an expression that is e to the minus lambda I minus lambda j. And here I see that is factorized into part that only depend on I and only depend on j. So let's see. So if I'm working this hypothesis that e to the minus lambda I is much less than 1, so I can approximate Pij just like the product of e to the minus lambda I, e to the minus lambda j. And the constraint will be that the expected degree is the sum over j from 1 to n of the marginal Pij. So I substitute the expression of the marginal here in this approximation, which will be e to the minus lambda I minus lambda j. And the part only depending on I can put it in front of the sum. So I will have e to the minus lambda I q, where q is nothing else as the sum over j between 1 and n of e to the minus lambda j. So now if I go and look at this expression here, I see that I can express e to the minus lambda I as ki expected over q, and when I substitute, and I can substitute this expression here in the equation for q. Okay, so now I have this self-consistent equation for q, in which there are only the degree that I'm enforcing and q. So this is the equation that I had before. So I can write q squared is equal the sum of all degree, which is k average n. And so q is square root of k average n. So I go back to the expression of e to the minus lambda I, which was ki over q. I substitute the square root of k average n, and I find again that in this marginal probability, Pij is nothing else than ki kj over k average n. And if I want to control what is the assumption I was starting from, that was e to the minus lambda I much less than 1, this assumption is nothing else than my expected degree of node I should be much smaller than k average n. So we said, you know, that we need to have at least the structural cutoff to see that the uncorrelated, the maximum entropy network, the canonical network ensemble, will become an uncorrelated network if the maximum degree of the network is much smaller than k average n. So at most, is at least it should satisfy the structural cutoff. So it's really the presence of this high degree node that induce the natural correlation that you see in the canonical ensemble. If you impose this sparsity with this bound on the maximum degree, you can get an uncorrelated network. So in this limit, we can really go back and consider the entropy of the ensemble. So we have the probability of each graph is just factorized into the probability of having each link. So each link occurs with probability I in j and is independently drawn with this probability. So the entropy is just the Shannon entropy constructed with this probability of PA and can be expressed just with the marginals. Sum over minus sum over I less than j, Pij logarithm of Pij, okay, sorry, plus, yeah, there should be a plus. No, okay, no, sorry, this equation is a kind of mess up. So it should be plus and there should not be this other sum in the middle. Sorry for that. So here it is. This is the correct formula. Sorry for that. So if you insert k average kj over k average n into this formula, you get the expression of the entropy in terms of the expected degree. And this is what happens if you have the uncorrelated limit, in which you can express Pij in terms of the expected degree in this form. And then you can practically, you might want to show that actually this entropy as a term that is non-extensive, it goes like n log n, but this term depends only on the average degree. So it's not informative of the degree sequence. And then there is a term that goes like n, which is instead informative of the degree sequence and distribution. And then there is also a sublinear term. So this can be proved by starting from this expression and assuming that the probability Pij is small. So x is ki kj over k average n is assumed to be much smaller than 1. Then you can expand the logarithm for small x and 1 minus s logarithm of 1 minus x for small x, and you get essentially the expression that we saw before. So interesting, you can also relate this expression of the entropy to the expression of the entropy we found for the random graph with the same expected degree. And you find that the entropy of an ensemble with given degree, expected degree sequence is given by the entropy of the random graph with the same average degree. And then there is a contribution that instead depends on the fact that the degree sequence is different from the one of a random graph. So this is this second term is the important term if you want to understand how the entropy change if you just change the degree distribution or the degree sequence. And so you have this expression that the entropy has this non-extensive term, but it's just a term due to in some sense, to the average degree, to the sparsity of the average degree, and is the entropy of the random graph with the same average degree. And then you have this important term instead, which depends on the degree sequence. So it's ki logarithm of ki. And then this term that depends also on the second moment of the degree distribution. And the second term can also be diverging. For instance, for scale-free graph, the second moment of the degree distribution diverge, but in presence of the structural cutoff, it diverge, is sublinear with n. So now I want to discuss a little bit with you the fact that in this canonical ensemble, in which I enforce the expected degree of the node, and I put myself in the uncorrelated limit, then practically the degree of each node might fluctuate because we are not in the art constraint. The degree of each node can fluctuate, but in average we'll have the value that I want, k bar I. And what is the distribution of this degree that fluctuates? The distribution is essentially a Poisson distribution with expected value, the degree that I want to impose, so bar, ki bar. Okay, so the probability that my node I will have degree k is the Poisson is given by the Poisson distribution with expected value k bar I. So I want to give a little bit into the detail of this proof, but this will not be examinable. But I think it's interesting to see this a little bit more involved derivation, because it can give some insight of some formula that is more complex that we will see later on for the microcanonical ensemble. So in the proof, we will use one expression, which is an identity, and is the integral expression for the Kronecker delta. So the Kronecker delta is a function that takes to discrete variable, and if they're equal is 1, and if they're different is 0. And you can express it in Fourier space in this way. Then we will use the Taylor expansion for exponential and the expansion for the logarithm 1 plus epsilon x approximated by linear approximation, first order approximation, like epsilon x for epsilon much smaller than 1. So we want to prove that the degree distribution of a node of degree k is given by the Poisson distribution. So practically, we are asking what is here the probability that the node has degree k. Here I use p of k, but this is the probability that node I has degree k. And what I do, I consider the average over the ensemble, and I impose that the degree with the Kronecker delta, then the degree of node I, which is expressed in terms of the adjacency matrix, is equal to k. So this will be the probability that in the ensemble my node has degree k. So here I can sum over all the elements of the matrix element, but all the elements which are relevant, because this the probability of the ensemble is in the ensemble, every link is drawn independently. So I sum only over the row of the adjacency matrix, so practically that indicates if node I has a link with node 1, with node 2, with node 3, and so on. I use the integral expression of the delta. I substitute the Kronecker delta with this integral expression, and I just here change the order of the sum and write integral in the omega e to the omega k, which is independent on I and j, and here I put e to the minus omega I omega sum over j aij. Okay, so I need to do this sum over the element matrix element, and here practically this e to the minus omega aij is just a set of factor that depends on ij independently. So I can just write this as the product over J between 1 and n of 1 minus Pij plus Pij e to the minus I omega. Okay, because here when practically I can invert the product with this sum of every matrix element, and I can express this in this way. Now this is e to the sum over j of the logarithm of this expression. So I have that the probability that my node has the degree k is given by this formula. I use the expansion for the logarithm for small Pij. And so when I sum, given that I use this expansion, I have sum over j from 1 to n of Pij, which is nothing else than my expected degree. And I have this expression here. So this is this quantity here inside the integral. So I just need to do this integral at the end, where I substitute this sum here by this quantity here. And when I do this sum, here I have this term e to the k average n multiply e to the minus I omega. I use the Taylor expansion, and then I do the integral term by term, and I get the Poisson degree distribution. So just to show you that this is, it is a little bit more involved than the previous calculation that we saw, but is totally understandable. Okay, how we get there. It's totally transparent. Okay, so this concludes. This was like a small addition to this canonical part, but really the take-home message is that in the canonical ensemble you can have a degree of a node that in average is fixed to what you want, k bar I, but it can fluctuate, and actually the distribution of the degree of that node is a Poisson distribution with average k bar I. So let's now turn into the discussion of the microcanonical ensemble, and in particular what is called the configuration model. So in the configuration model, you want to construct a network with given degree sequence. So really you want to consider only the network that really satisfy the degree sequence as a hard constraint. So you have practically, you assign to each node the degree that you want that node to have, and then you really need to match these tabs in a way that you form a simple network, so a network in which there are no multiple edge, there are no tadpole, and it's a simple network. And in this way, you really construct a network with the degree sequence that you like. So one thing you need to be careful is what is called graphicality. So a degree sequence is graphical if it's the degree sequence of at least a simple network. And here I have a question for you if you want to answer. So not all the degree sequence are graphical, and in particular there is a condition that is very easy to understand that you need to impose to the degree sequence to be graphical. And this comes from the fact that every link increases the degree of one node and of another node. Okay, so if you have just one link and you sum the degree of the first node and the degree of the second node, you get 2, right? So can you expect a condition that you might, and if you have another link, you also add the degree, 1 to the degree of one node and 1 to the degree of another node. So really, if you have a degree sequence where sum of the degrees is odd, you will never be able to find a network that satisfies that, because practically a link increase the degree by 2 at the sum of the degree by 2 at each time. So you can never have a sum of the degree that is odd. This is a trivial condition that you need to impose to your degree distribution to be graphical. And in general, there is even more strict conditions. So it's not just this thing that should be avoided, but there is this strict condition which is described by the Erdős-Galay theorem. So the Erdős-Galay theorem will tell you, given a degree sequence, will tell you if there is at least one network which satisfies the degree sequence. So in order to have a configuration model, you need to start from a graphical sequence. One thing to do, a solution to the graphicality, is that you can have a degree sequence and you can check with the Galay theorem if it's graphical. Another way to go around is that you can start with the degree sequence of an observed network. So you want to find all the networks that have the same degree sequence of a network that you observed, a real network that you observed. So you know for sure that at least one graph satisfies that. Or you start with a degree sequence, but you allow, you know, if you allow some small modification of it. Okay, so you allow a minimal set of deviation from the degree sequence that you have. So how can we generate the configuration model? There are code available online, but essentially you start with the degree sequence, you assign these stubs, these half edges to each node I, and then you really randomly match these stubs. The fact is that this algorithm can get stuck, so you can generate tadpoles, so node links that connect the node to itself, or you can generate multiple edges, so 2 links that connect the same pair of nodes. And if this occurs, you just need to start all over again and redraw your network from scratch. So you start like this. You have these stubs, you have the degree sequence, the stubs, you randomly match the stubs, and here you find, for instance, one tadpole, node I one connected to one, and one multiple edge, node 5 and 2 connected by 2 links. This is no good. So this is a tadpole and a multiple edge. So this network should be disregarded. You can start disregarding this as soon as you get a fast tadpole or a fast multiple edge. So what you need to do, you can restart from the beginning, not just backtrack 1 or 2 steps, just start over from the beginning and draw and redo the procedure until you find a network that is simple. Okay, so this procedure might be quite long, and but in any case, if you start from a network with the structural cutoff, this procedure is typically much faster. So then you are asking yourself, what is the relation, right, between the entropy of this ensemble, of the microcanonical ensemble sigma, and the entropy S of the canonical ensemble, in which the expected the constraint is in the degree sequence in expectation. So you constrain the expected degree sequence, and the difference is essentially that sigma is related to S by this quantity omega, which is equal, as we discussed in previous class, to the minus the logarithm, the sum over all the adjacency matrix, the probability of a network given by the adjacency matrix A in the canonical model, and then you sum all the probability of all the network in the canonical model that satisfy the art constraint. So you put yourself in the canonical model in which the degree of each node might fluctuate, and you ask yourself what is the probability that these degrees take exactly the value that is the art constraint. So interesting, if you are in the uncorrelated limit, this omega has a very simple expression. This is the sum over I between 1 and n of the logarithm of this expression here, that is nothing else than the value of a Poisson distribution which average ki calculated exactly at ki. So what is the meaning of this expression? So here you have practically your canonical ensemble in which all the nodes can fluctuate. The degree of each node is a Poisson distribution which have average ki, k bar I, the one that I want to impose. And I'm asking what is the probability that in this ensemble all the graph, all the nodes satisfy the art constraint. And omega is nothing else than the logarithm of the probability that each node really that can fluctuate, the degree that fluctuate, as exactly the degree that is this average degree. Okay, so because the k bar I in the canonical ensemble will be made exactly the same as the art constraint in the microcanonical ensemble. So what is the take-home message from this? Omega here is a sum of n term. So it's a quantity that grows with the network size linearly with the network size. So it's extensive. So it is comparable with important term in S, in the entropy of the canonical ensemble. So it is not negligible. And this means that these ensembles are not equivalent, are not thermodynamically equivalent, because their entropy is different. And more specifically, if we want to capture a little bit more intuitively this difference, we can consider a microcanonical ensemble of regular network in which we impose that every node has an average, a degree which is exactly k average. So for instance, every node has exactly degree 5, and a canonical ensemble in which we impose that every node have in average a degree 5. So the canonical ensemble is a Poisson network in which every node fluctuates as a degree, which is following the Poisson degree distribution. And in general, the probability is that in the network I find a node of degree k follow the Poisson distribution. In the microcanonical ensemble, every node has exactly degree equal to 5, to the average degree. So these two ensembles are really different, and this is reflected in the fact that the entropy of the microcanonical ensemble sigma is smaller than the entropy S of the canonical ensemble. Interesting, with this expression, we can go back to a very famous formula by Canfin and Bender, which find the asymptotic number of network with given degree sequence. which is given by this expression. Okay, so this expression can be extracted, can be understood as this k average n double factorial is the number of possible matching between half stubs. This product on I of ki factorial is the degeneracy of counting due to the permutation of half stub of each node. So if here I have 3 nodes and one stub match a stub of another node, I can permute these stubs and have the same network essentially, but the matching is different between the stubs. So I want to divide by this degeneracy, and this other term is a term that is understood as a term that corrects for the probability of observing multiple edges and in the network. So this expression can be actually rederived starting from this expression sigma is equal S minus omega, where S is the entropy of the canonical ensemble, in which the soft constraint that we impose, k bar I, are equal to the hard constraint that we are imposing in the sigma in the microcanonical ensemble. So we can remove this bar on top, and omega is just equal to this expression we have discussed above. So we can use Stirling, we can use, just develop this logarithm. Use the probability, we are not using Stirling here. And so sigma is given by this expression, and the asymptotic number of graph in the ensemble is e to the entropy of the microcanonical ensemble and is scaling according to the Bender and Canfield formula. So we have this beautiful formula that tell us a little bit about the combinatorics behind this matching. Another important thing that we get is that actually this entropy of the microcanonical ensemble depends on the degree sequences. So not only depending on the average degree, but depends also on the degree sequence. And different network with the same average degree, but different degree sequence might have a different entropy. So here, for instance, I have two network consistent with the same number of links, I think. And in one network, I have only one way to, in one distribution, degree distribution, I have only one network that I can construct, a star. And in the other scenario, with the other degree distribution, I can construct a network in at least two ways. So the same, the degree distribution can be in some sense corresponding to the fact that I can construct the network in more or less I can have more or less freedom to construct a network starting from a given degree distribution. So some degree distribution are constrained more the ensemble. So they, and you know, if I have a star network, I can construct only one graph. If I have more homogeneous degree distribution, I have more freedom to generate different networks. So interesting, if I put the scale-free degree distribution as an input for this ensemble, I see that the entropy of the ensemble decrease as gamma decrease, meaning that if the network distribution, the distribution becomes broader and broader, so I have more high degree node, more hubs, more kind of locally star-like structure, then I'm reducing the number of networks I can really construct. Okay, so this is there is more information in the degree distribution if the degree distribution is very heterogeneous. So finally, a final remark, we have spoken about randomization and edge swap, and the edge swap are very useful and I use quite broadly, but actually one needs to know that they provide a bias sampling of the configuration model. And if you want to have an unbiased sampling, you need to have to construct a metropolis Hastings algorithm, where here when you define the probability of accepting a move, you have to consider the probability of the network that you propose, divided the probability of the network from which you start, and you have to multiply by this other factor, phi a over phi a prime, where phi a indicates the number of viable edge swap allows starting from a given adjacency matrix A. So there is this little term that is actually important and that makes edge swapping without considering this term a bias randomization, however, very, very widely used. So if you want to be consistent with a lot of literature, as long as you know that they contain a bias, you can still do it. So yeah, so I am quite quick today. I want to finish this class by, then we can discuss a little bit more in detail if you have questions. I want to finish this class by telling you a little bit about the local structure of this ensemble with given degree sequence. So we have seen that in the random graph they have in the Poisson limit, if they're sparse network limit, they have really negligible, they are locally tree-like, they have a negligible number of triangle and small cycles, small loops in the network. So in particular, the number of triangle is finite as the network size is infinite. So this means that they are really really negligible. And if the degree distribution of the network is not Poisson, so if you are enforcing, for instance, a scale-free degree distribution, then you can find a significance deviation respect to this scenario. And the number of small loops becomes given by this expression, where here you see that there is an emergence of a second moment of the degree distribution, so something that diverge for scale-free graph. And so you can have many more local triangle, square, pentagon, small loops where L is finite and the network is infinite. So you can have infinite number of small loops. However, this number, and this is an expression in the uncorrelated network limit, this number will be subextensive, meaning that if you want to calculate, for instance, the clustering coefficient will be always vanishing in the large network limit. So with scale-free graph, we are increasing the number of loops locally in the network, but still the network does not have, every node does not have a finite clustering coefficient, but still have a vanishing clustering coefficient. And interesting also, scale-free graph can also have quite an extensive number of cliques, and the cliques of size C are the average number of cliques of size C is given by this expression. And by analyzing this expression, you can see that practically a sparse network, a scale-free network, which is sparse, can have the largest cliques that diverge with the network size also, while in Poisson network, if the Poisson network is sparse, the largest clique is only a triangle. And you need to require for a Poisson graph, for a random graph, in order to have cliques of more significant order, you have really to require a density of links that scales more and more fast with the number of nodes in the graph. So this is just to mention that this random graph in which we enforce the degree sequence and is not and they are not Poisson graph might be very different also locally with respect to random graph. So with this, I reach the conclusion of this second part of the third lesson. And in this second part, we have covered canonical network ensemble in their uncorrelated network limit. So how we can express the entropy of this ensemble in the uncorrelated network limit. And we have seen that there is always this non-extensive, super extensive n log n term, which is the same as the one for a random graph with the same average degree. And then we have an interesting term that depends on the degree sequence, and that captures the fact that the entropy of the ensemble depends on the degree sequence of the network. And then we have discussed the microcanonical ensemble, the construction of this microcanonical ensemble, which is also well known as the configuration model, the problems of this algorithm, the problems connected with graphicality, the fact that the algorithm for building a configuration model can get stuck to this undesired configuration, having multiple edge and tadpole, and how you can avoid these problems. And then we discuss a bit more in general this result of the non-equivalence of the ensemble. And then in the next part in the next lesson, not in the next part of this lesson, next lesson, we will introduce maximum entropy model with latent variable, and in particular spatial network and block models which have communities. Okay, so this concludes the part 2 of lesson 3, and I now stop the recording and waiting for your questions.